Okay, for our main presentation tonight, it is my pleasure to introduce Walt Cooney, who is all into the science part of the hobby, and he's also introduced me to that part of the hobby too, me being an astrophotographer. So that's saying something there. So Walt is a retired chemical engineer. He's been an amateur astronomer for a really, really long time. Was also involved in some of the astro research that was going on earlier, even though nowadays that's difficult. Co-authored many papers. He is a section co-leader of the AAVSO, which is the American Association for Variable Star Observing. And he'll be getting into a little bit more of that. He was a past president of the Baton Rouge Astronomical Society, is a Houston Astronomical Society and AAVSO board member, and also has an asteroid named after him.
I'm jealous. His is lower numbered than mine.
Oh, his number's lower than yours. Oh gosh, yeah, that's pretty cool. And the other thing about Walt is he's also been a gracious mentor to our club in helping us starting our own variable star research. So I really appreciate all the patience Walt has had with Liz and myself and getting started. So Walt, without further ado.
Thanks, I appreciate it. And it's funny you say that because there really is kind of a competition. Well, my numbered asteroid is not, you know, as ridiculous as that is. Anyhow, okay, so presentation on cataclysmic variables. And these are stars that undergo cataclysms. A lot of different kinds of cataclysmic variables. We'll talk about a few of them. And particularly we'll talk about the one that is got people very excited right now. It's T Corona Borealis, and it's a recurrent nova that's getting ready to go again for the first time in almost 8 years. And so we will talk about that. Cool. Okay, but first we got to start with a little history. Archaeoastronomy, the history of astronomy is really pretty neat. There's awfully great stuff in Sky Telescope and astronomy nowadays about that. And a little bit, supernovae are the ones that have gotten the most attention in the last multiple thousands of years. And the oldest record that we know of now, at least we believe, is on this stone in India. And there were a lot of theories about what that is, but now they believe that this is the sky well, we think it corresponded with 3600 BC when this supernova went off, because this is Orion, their version of Orion is Taurus. This is, I think this is part of Andromeda, and Cepheus up there, they had different names for it. And then one of these is the supernova. One's the sun, one's the supernova, and honestly, I don't remember which. But that's 3600 BC and the earliest record we think. The Chinese, of course, we all know the reported supernovae. This is a document from China recording the supernova of 1054, aka the Crab Nebula, when it was just a big bright daytime star. And then in 1604, Kepler's supernova was reported in this star chart in a book, 1606 book. And so this is their depiction of constellation Ophiuchus. And right down here, there's this bright star with a big N next to it for nova, or a new star. And that's correct. That was Kepler's supernova. That's where it is down at the foot of Ophiuchus. So pretty cool stuff. And I wanted to show at least a few pretty pictures. And this is a supernova remnant, and it's actually infrared. And so, these aren't our normal colors. Our eyes are not infrared enabled. We haven't found that switch just yet. It's 8,000 light years away, 85 light years across. And this star peaked at magnitude -8. And so, as you know, Venus at its brightest is about -4.7, and it's visible in daytime, but with a trick or two. Really, you end up having to put a house to the side so you get a little bit of shade. But you can see Venus in the daytime on a clear day, and so -8, you could definitely see daytime sky. Bill,
Did we see that star?
I didn't.
I mean. And then it was, that star visible, the supernova visible, was it recorded?
Yeah, I don't know. Maybe, but I really don't know. 185 MeV.
Oh, okay.
So, yeah, that's supernova 185. So, and Centaurus is a more southern constellation.
yeah.
So I don't know if the Chinese would have been able to see it or not. for
Okay.
instance.
Probably not that.
Yeah, so.
Maybe Australian.
Yeah, right. Here's another one. This is in 1006 in Lupus. It's 7,000 light years away. It's already 60 light years across. So 7,000 years ago, it was just a star. Now 60 light years across, it got to -7. So it can also be seen in the daytime. And the Crab Nebula, you may recognize it. 1054, 6,500 light years away, 11 light years across. It hasn't grown as much as some of them yet. -6, so it was also visible in the daytime.
What? I just have a question,
Yeah.
maybe. How did it determine when it went supernova?
How do they determine when it went supernova? Well, some of them we have records. Some of them we can go back and run the movie in reverse. And I'll show you what I mean here in just a second. So this is Tycho supernova in 1572 in Cassiopeia. And 9,000 light years across. I'm sorry, 9,000 light years away, 25 light years across. -4, maybe, probably not really visible daytime, but as bright as Venus in the nighttime sky. What's that?
If we could have another one of those, I'd take it.
Yeah. But so this is a cool picture because this was a type 1A supernova, and so it's a binary star, and the white dwarf is what went kablooey, and it leaves behind the second star of that system. And what's kind of interesting is, the center of this nebula is something like this, but there's nothing there. And so some recent work, they figured out that this is that remaining star. And so when the system was blown apart, they're orbiting each other. And so all of a sudden, the mass that was holding them bound part of it has blown away. And so that companion star now is free to sling off in the direction that its orbit was taking it. And so it's off center. And that's a Hubble Space Telescope picture.
Oh, that star is.
It's moving. Yeah, and I say slinging, which isn't really the right word. It doesn't sling, it's just freed. And if the Earth instantly worked here, the moon would keep going whichever way it was already going. So maybe that's a better explanation. But if you don't mind clicking that link down here, and we'll just see if this works. Okay, so this is a time lapse of Tycho supernova from 2000 to 2015. And you can see that the remnant is still growing, and that's pretty amazing. And so you can do things, you can either use the time lapse like this, or you can use spectroscopy to figure out what the velocity of this material is, and then you can bring it back to when the supernova happened.
So we're saying the white dwarf was accreting from the companion, and the companion
Yes.
got free?
Yeah, the white dwarf was accreting from a companion. The white dwarf exploded, and the companion then just took off in the direction it was headed,
Okay,
give or take.
get out of that.
Yeah, and actually, we'll talk about that here in just a second. Let's go on to the next.
There could be a potential black hole there.
I'm sorry?
There could be a potential black hole there.
No, nothing about
Black hole.
Yeah,
White dwarf doesn't have enough mass.
Yeah.
I think that's right. They don't.
It's 20 solar.
Yeah.
Two supernovas.
Okay, so I have to do the next one here. There we go.
Okay, another pretty picture. This is, we saw Kepler supernova in 1572. They had a good run going, because just a few years later, 1604,
How's it going?
Tycho's, yeah, sorry.
You need anything?
Did I hear something?
Hello?
Online.
Are they muted?
Somebody on Zoom.
Okay. And so Kepler supernova in 1604, and here's some pictures of it in different wavelengths. And some close-ups of that, 20,000 light years away, 10 light years across, magnitude -2.5. And so this was more like Jupiter in terms of brightness. So. And I had to show this picture. I think this is so neat. Some of you may remember that in 2011, we had a supernova in the Pinwheel galaxy M101. It got up to 10th magnitude. You see in the telescope, a lot of people saw the telescope. It's really neat to see a supernova and realize what it is in a galaxy that's bright as a Messier galaxy. And then it was kind enough 12 years later to do it again, but now it's over here. And the first one was a type 1A supernova. And so that's two stars rotating around each other where the white dwarf is blasted to smithereens. But the second one is a type 2 supernova. And so that's a core collapse supernova. And yeah, maybe that can go to a black
That
hole.
can go either neutron star or.
Yeah,
black
yeah.
hole.
I have to admit, that's not my expertise.
I think the 1As are too small to make black holes, but the 2s can be.
Yeah, makes sense.
Hey, two is a bigger rare.
Okay, so those supernovae are the big hitters when it comes to cataclysmic variables. That's the biggest cataclysm we've got. But there's lots of others. There's a whole zoo of different cataclysmic variables. And I'll mention a few of them here. Recurrent novae, dwarf novae, nova-like variables, polars, intermediate polars, ZCAMs, and the list goes on and on and on. And luckily, I have a slide of all 2,000.
We'll go off, we'll each way.
Next. Okay, so what are they? I talked a little bit about it. These are binary star systems with the lone exception of type 2 supernovae. All the rest of these cataclysmic variables are binary star systems. And the way to think about these is, I'm sure many of you have read about the life and death of a star. And so cataclysmic variables come about in the life and death of a double star. And if the stars are very far apart, then they go about their business and they go through their life and death just like they were alone by themselves in the galaxy. Although the majority of stars in the universe are actually binary or multiple, lone stars is actually a little bit less common. So anyhow, and so if the two stars happen to form and they are close together, then how they grow old and die changes a lot. And the little bit of geometry to understand about this is what's called the Lagrangian surface. And so if you've got two stars, then you can draw this kind of a dumbbell shape around them, which is the equipotential gravity surface. All that really means is anything that's within this surface belongs to either this star or that star or neither star. Okay, and at this point here, the L1 Lagrangian point, it belongs to both stars equally, and so that's where mass from one star could easily slide over to the other star, and that's what happens. So as the more massive star in a close binary system grows old, it grows old faster. Larger, heavier stars age more quickly than smaller ones. And so the large star will actually expand to the point where it starts to overflow into the other star. Now, I'm cheating a little bit because actually it happened in reverse first. So let me show you. This is just a pretty picture. This is the donor star, it's often called. The white dwarf is here in the center. An accretion disk of matter that has gone through the Roche lobe and is slowly spinning down into the white dwarf. And I say spinning down for a reason. The matter that comes off of this star can't just take a direct line to the other star, because there's a lot of angular momentum, a lot of rotation going on in the system. And just like energy is conserved, mass is conserved, angular momentum is also conserved. And so it has to take a spinning force down into the white dwarf as it slowly derotates, as it slowly loses that angular momentum. And so that's why we end up with an accretion disk.
Has an accretion disk ever been imaged?
Yes, I'm sure. I can't think of a particular image.
We just did with the when the black hole was imaged last 2 years ago. That was the accretion disk around the time. The Sagittarius is.
Well, yeah, although it was a little different system, but yes, to talk about the accretion disk around the black hole, we've seen these two images, one from the Milky Way's black hole and the other one from M87. And that, you're right, that's an accretion disk that's going down into the black hole. A little bit different system, but same kind of thing.
One quick question.
Yeah,
How close do the double stars have to be in order to have this variable star?
yeah, it depends. There's quite a range. Typical cataclysmic variable, this is going to be something like the Earth-Moon distance.
Oh.
Now, not necessarily. There's one, as a matter of fact, T-Core-Bohr. This star is a giant, and the orbital period is something like 250 or 280 days. So it's not Earth-Moon, it's more like Earth-Sun. But they're really quite shockingly close. Typical orbital periods can be on the order of hours to a day or two. I won't go through this. This is a graphic that you can find out there. This is how these stars really start off as an innocent pair of binary stars that then go through this process. But the one thing I wanted to show you is that they do flip. So and they've drawn this to me a little bit confusingly too. They don't keep the stars always on the same side, but the more massive star grows older first and swells, just like our sun will do in 4 billion years, give or take. And when that happens, it overflows that Roche lobe, starts spilling matter onto the other star. That goes so far that they end up inside a common envelope of material with those two stars spinning inside of that. Finally, that common envelope is blown away. And at this point, what has happened is enough material has come off the giant star that the smaller star is now bigger. And yeah, okay, no, that's right. It is the original star that first grew old is the one that does eventually become the white dwarf. But then what turns around is now it's the star that was the smaller star that gets older, and it goes over its Roche lobe, and so now the material has turned around and is going in a different direction. You know, first it was from this as a giant going to this one. It blew all that matter away. This became the white dwarf. This got older, and now the material starts going in the opposite direction. And then at some point, enough material comes over that this star, the white dwarf, reaches its Chandrasekhar limit of about 1.4 solar masses. And at that point, it can't support itself, and thermonuclear fusion destroys it. It's completely obliterated. So,
I have a question. How
Yeah.
What causes the common envelope to be affected?
what causes the common flow to, or the common envelope to
Be affected?
to be ejected? Yeah, yeah, I don't know. You know, there's always a substantial amount of what we would call solar wind in our solar system that's blowing things away. I'm sure ultimately this isn't very stable. Some of it's collected in the two stars that remain, and the rest of it is just blown away. And I think it's as simple as that. So. Okay, so we talked about supernovae, 15 to 20 magnitude change in brightness, just enormous amounts of energy. Okay, but there's one thing that's interesting about so this is why we believe supernovae, type 1A supernovae are standard candles, because you always get this 1.4 solar mass explosion. So it's always the same stick of dynamite. It's always the same firecracker. And that's why it's a standard candle. But there is another way to get past the Chandrasekhar limit, and that is when two white dwarfs merge. And we believe we've seen this. And so, for instance, if a 0.8 solar mass white dwarf and a 1.1 solar mass white dwarf collide into each other, spin down and get together, now they're well over the Chandrasekhar limit. And so how can it still be a standard candle if it's not the 1.4 masses, solar masses that's going up? And I have an answer to that, that is a good question.
I vote that they be called 1Ds now, okay?
Yeah, there are lots of different type 1As that, we've learned a lot about this, is that they're not truly standard candles, that there are differences. And over the last 10 or 20 years, as we've delved very, very deeply into this with things like the Hubble Space Telescope, et cetera, we have found out that, yeah, they're not perfect standard candles, and there are some things going on, and there's still many things that we just plain don't understand.
Don't they look at light curves to determine some of what is what? Yeah.
They do. Between light curves and spectroscopy, they can learn a lot about these. In particular, for the light curves and supernovae, they can be faster, slower. They can have different activity as they fade away, and so there is a lot to be learned that way. It's one of the ways that they can show that, well, they can't be standard candles because they don't all act exactly the same way.
Yeah, and since the standard candles are used for determining, the ultimate fate of the universe.
And that's the question. This back in 2010-ish, a bunch of people got Nobel Prizes for the work they did with supernovae to show that the expansion of the universe, to show dark energy, all that kind of stuff. And it's a little embarrassing that their standard candles aren't. The work is still good. There's just still a lot more we don't understand. And you do have to wonder how this might factor into the Hubble tension, if you're familiar with that. So different measurements. Supernovae measure a certain speed of the universe expanding, versus the cosmic microwave background tells us a different number. And at first, the error bars on those two numbers were like this. So it's all right, that's, they're probably okay. And then they put in a lot of work and got better and better answers, and the error bars have done this. And that was not the intended effect here, but that's what happened.
And in 20 minutes, it's gonna change again.
Yeah, that's right. What time is it?
So,
So,
the more we know, the more we know that we don't know.
oh, gosh. Yeah, that's very true. So, and so let's go on a little bit, so I will go ahead and skip this. There's a Large Magellanic Cloud, was a type 2 supernova in 1987. And then switch over to Novae, not quite as powerful, still same kind of thing, binary star system with a white dwarf and a more normal star. They only go a minuscule 7 to 15 magnitudes brighter, so a lot. Their mechanism is different. The white dwarf isn't exploded, isn't destroyed. What happens is hydrogen builds on the surface of the white dwarf from that accretion disk until it reaches a temperature where it goes thermonuclear and blows off those outer layers from the white dwarf. And so it's not as energetic. It's not the entire white dwarf going to blue. It's just outer layers. But and the white dwarf remains behind. But here's another thing that we don't really quite understand. When that outer layer of hydrogen that has been accreting over years goes thermonuclear and blows off, some of the underlying material in the white dwarf goes with it. And so the result is the white dwarf is smaller. And so how does it build matter to get to the 1.4 solar masses if it gets smaller when it goes nova? And again, good question. Yeah. So there's still a lot we go saying. We have some theories, and it's argued, and they can't say they know that answer. These are really cool. Novae, at least 10 of them in our Milky Way galaxy, that's all we discovered so far, go nova more than once, recurrent novae. And some of you may remember in 2021 was RS Ophiuchi went nova. And then last year, no, 2022, 2 years ago already, U Scorpii was a recurrent nova that went nova again. But this is the one that everybody's really excited about now. T-Core. It's been since 1946 when it last erupted. And we've got really, really great predictions right now that it's going to go in the next 6 months or so. And I'll show you.
A quick question, sorry.
Yeah,
What's the difference between Novae and the supernovae?
I'm sorry.
What's the difference between Novae and the supernovae?
Yeah, okay, so supernovae is where you reach the white dwarf somehow reaches that 1.4 solar masses and it completely explodes. But a nova is just the buildup of material on the surface of the white dwarf that reaches a high enough temperature where just that surface material, the surface portion, explodes. And so it's a much smaller amount of material, and the white dwarf is still there when you're done. It has not exploded.
So it's time to take our before pictures now.
What's that? Sorry.
It's time to take our before pictures.
Yes, yeah, well, a lot of people are. So for T-Core Bohr, again, if you like this archaeoastronomy stuff, Dr. Brad Schaefer is an emeritus professor of astronomy at LSU. And he loves the archaeoastronomy too. He's gone back into monastery papers and that kind of thing. And he's pretty confident that he has found 2 previous eruptions of T-Core Bohr, one in 1217, one in 1787. Pretty cool. He's the one who's got this prediction now that's gotten it in this type, and I'll show you why here in a second.
So if it's 80 years, I would have thought somebody in the 1700s would have seen it, like in 1786 and 1700, or they not?
We are missing some. We don't know why that is. One possibility is it was behind the sun.
Yeah.
And then novae don't get quite as bright as well. You know, this one gets up to about second magnitude, which is great, but not -8, where you can see in the daytime.
Based on my experience, I know what happened. It was cloudy that day.
It was.
Well, let's move on, telescope that.
There's something to that actually, because T4 board, and look at this, it fades very quickly after it goes nova. Within a week, it's lost 3+ magnitudes.
Very close.
And so there you go. And if that happened when it was behind the sun, I think Corona Borealis is north enough. It's for some places, it doesn't really ever quite go behind the sun. But still, they weren't writing things down, I guess, about it at the time. So here's some particulars. So what we think about this one is that the white dwarf is about 1.37 solar masses. It's an oxygen neon magnesium white dwarf. There's several different kinds of white dwarfs. The secondary, the donor star is about 0.8 solar masses. 228-day orbit. Okay, I had that not quite right. Half an AU separation, and about 2,500 light years from Earth. So this is the graph. This is how we can make this amazing prediction. This is from a paper that Dr. Schaefer has recently published, and this is the Let curve of T4 board since 1866, 1855, actually, but I think 1866 was that previous eruption. And so the green circles are either visual eyeballs or photography looking at green wavelengths. And then these blue circles are photometry or photography looking specifically at blue wavelengths. And Dr. Schaefer's gone back into the old Harvard plates and measured a bunch of these numbers. So, but here's what you see. So this is when it went off in, I think, 1866, went all the way to second magnitude. In 1846, did it again, but there's this. Sometime roughly about a year before it went off, somewhat in green light, but particularly in blue light, it rose, what is that? More than a magnitude in brightness. And it sat there. And then right before it went off, it dropped back and then blew. So this is what's going on now. It actually started, it rose, you know, that initial thing I showed? Well, I said 1 year. It's more like 4 or 5 years or something like that. But it in 2016 is when we first noticed in particularly in blue that it came up about a magnitude. And it's been sitting there since then. And then last spring, pay no mind, I can explain these those curves here in a second, but this is what it should be doing. And last spring, it stopped following its pattern, it dropped off in blue. And so if history repeats itself, and there's no reason why it shouldn't, it's about to go. And so this is today's data. I went and got this off the AVSO website this afternoon. And let's see, so this is last spring. So it's still got these waves. That's something else entirely we can talk about if you want. But it's way down. And it's still way down. As of 6:31 a.m. this morning, according to Brandon Sandel, it was still at 9.7 visual, which is where it's been. Bill?
No,
You're just counting
good point.
11, 12, 13, 14.
So, what, just out of curiosity, why is there an increased density? Is it because more people are reporting?
Yes, yeah. Extra points are more people. This is when people really got to be excited about it. This was back when Brad had made his prediction, seeing this. He started talking about it last summer, and I guess actually, okay, so this is really last spring. this is when it dove. This is when Brad raised the alarm. And people started jumping all over it to see what was
So
going
all
on.
that stuff to the left that you're standing in front of there,
Yeah,
that's
this is,
already at the high level indicating it's getting ready.
yes,
But then the drop is the,
Right.
okay, hold your breath, here it comes.
oops, oops, oops.
But the 9.7 from this morning is off the scale.
Well, no, but that's visual. So that's the green,
Sorry,
and so that's actually about right. I changed colors on it. And so again, looking at it from this perspective, here's the last, what, 2016, so 8 years, 7, 8 years. It's been doing this. This is the last year. This is what it's doing, and of course, that's what we're waiting for.
Well, you can start selling tickets for it.
That's gonna be a good show.
You know, it is so lucky you said that, Bill, because I brought some tickets. And they are for you $1,000.
That's very nice.
We go too far back. So,
So it dove, when you say it dove, it actually dove in magnitude, it became brighter, right?
yes, it became brighter, and when it dove, it really kind of dove back to where it was.
So this is an inverse case, sorry.
Can you see that? So it got brighter, and then this is the dive, but really the dive just kind of put it back where it normally ought to be. So just terminology.
It gives you several years warning, and then another shorter warning.
You can look back in 2016 Sky and Telescopes and see them talk about, oh, wow. It's getting brighter. It's gearing up. So,
I remember reading about, I had like an old astronomy textbook when I was a kid, and I remember reading about T-Pro Borealis in 1946.
yeah. Well, and there's so much great history there. Leslie Peltier, if you guys know him, he wrote Starlit Nights, the amazing book. He watched this for years and years and years. So, and he was the one who predicted back in 45 or 46 or something like that, that it's getting ready to go. But then he didn't see it go. I'm sure he saw after the fact a little bit, but he didn't see it really go. He felt like T4 Board had cheated him. After all these years of watching it, it waited till he wasn't looking. If I remember the story, he rolled over that night and turned his alarm clock off.
Oh, man. How quickly does it go up?
Real quick. I don't know exactly. I haven't looked, but less than a day. And so, oops. That's what's so awesome about, now you can't really see it here because this is all compressed, but we really want to catch it going up.
Yeah.
Get some data points. So everybody's looking, hoping to be that person to catch it.
Yeah, it was cool.
This kind of modulation there, that's because the donor star is kind of teardrop shaped. And so when it's kind of, how do you do a teardrop? When it's kind of face on, it's bright. And when it's pointed towards you or away from you, you see less of the face. And so that's about a third of magnitude of ellipsoidal modulation is the term they use for it. So. Okay, a couple of words about other kinds. I said there's quite the zoo of cataclysmic variables. So they do lots of different things, really fascinating. There are things called, they have an outburst where they go off, usually just a few magnitudes for a dwarf nova, not 7, 15. These are dwarf novae, these are smaller. I won't go through some of the details here, but they do interesting things. They have something called a super hump with periodic brightening adjustments, and then they have flickering, and they do all kinds of other stuff. And so they're a gigantic laboratory, physics laboratory that happens on short scales, short time scales. And so we learn a lot from these, including what happens around the accretion disks of black holes. Just a few of the denizens of this zoo. So SS Cygni is a very well-known one. These are AABSO light curves. The green dots are photometry. somebody with a CCD or CMOS camera. And the open circles are visual estimates, eyeball. And I love this stuff because it shows you how great the eyeball work still is and how it's still important and still useful. And we don't have to spend any money on it. We come equipped with it. And the charts are free and submitting the numbers are free. And so this is, 10th magnitude, so a small telescope can do an estimate on this. We've got stars that are 4th, 5th, 6th magnitude. You can do it with binoculars or eyeballs, naked eye. But so this one goes into regular outbursts, and it's quite famous, quite interesting. This is called SU Ursa Majoris, and it was the first one, or at least one of the most important. So the whole type is called the SU Uma type. And it has all those outbursts, but then every so often it has a super outburst. And that's where super humps come in, and et cetera, et cetera. These are Z-cams. It also was important. It got to be the name for all of them. Z-cam Laperilus. And so it has outbursts. And then every so often on the way back down, it just stops and hangs. And it just kind of bebops around about that brightness for months, varying time scales. And then it'll say, all right, let's go do the outburst thing again. And it starts doing that, and then, well, it hangs again. And that time not as long as this time. And that's actually pretty recent there. So I didn't check today's data, but apparently it's still outburst waves. UX UMA, it didn't get its own kind. It's called a nova light variable because the spectrum, it looks just like an active nova. And what we believe these are cataclysmic variables that are always on. They're always in outbursts.
And they usually take a break.
Well, except the break in this case is an eclipse.
Oh.
And that's why I wanted to show this one, because the line of sight was good, so that this eclipse, which is what the full magnitude, maybe 8, 9 tenths of a magnitude, that's when both the white dwarf and the accretion disk are behind the donor star. And so this is the brightness of the donor star. And this is the brightness when they're all visible.
That is 2 days there.
Yeah. Yeah. Yeah, so they're just screaming. Yeah, some of them are faster than that.
So there's an occultation of sorts, right? An occultation right there.
Opposition.
Occultation.
Occultation. Yeah.
So the difference between the two dips would give the time period of rotation,
Yes.
because that's,
Actually, yes, and it's the full time period of rotation, because the half rotation, the white dwarf and the accretion disk would be in front of the donor star. And so you only have a small dip here because only a little bit of the donor star is being eclipsed. But the bright part is the white dwarf and the accretion disk. So yeah, that's the orbital period. That's what's so fantastic about systems like this, is we've got an absolute direct measurement of the orbital period, and we can watch that change. And so the data that we produce shows how that orbit is either getting smaller or getting larger. So, okay, polars are also neat. In this case, the white dwarf has a ludicrously powerful magnetic field. The sun's magnetic field is about 1 Gauss. The magnetic field of the white dwarf and the polar is between 10 million and 80 million Gauss. So the sun is just a piker compared with this. And that magnetic field is so strong that the accretion disk never forms. The magnetic field pulls the material up and out of that line, and then sucks it down through the magnetic poles of the white dwarf. And they call it a polar, not because it comes in the poles, but because this light is polarized. Yeah,
So do you think the, white dwarf is like made a lot of metal content in it for the magnetic field? So,
yeah, I don't know. Don't know. When you talk about metals in white dwarfs normally the highest, molecular weight or, atomic number of anything in a white dwarf is neon. And so it's not a metal like we think of metals. But it does say that there's just massive circulation going on because magnetic fields are generally the result of huge circulations of electrical currents. But this is my favorite. This is an intermediate polar. This is where this white dwarf, instead of 10 to 80 million Gauss, hits 3 to 10 million Gauss. And so the accretion disk does form. But partway down, the magnetic field is strong enough to now grab the material off the accretion disk and pull it in the poles of the white dwarf. And so you end up with a donut on accretion disk. And they do all kinds of interesting things in the light curves. This one here is another eclipsing light curve. That's what this big giant, these eclipses are. BQ Hercules. This white dwarf spins at 73 seconds, 71 seconds. And I know that because I can see it in my data. It's not hard to do, actually. Surprisingly, I can't actually see it spinning, but there some easy tools to show that to you.
Yeah, but you can see the brightness is changing over a period of like a little more than a minute.
Yeah, yeah, you really can. 71 seconds. Okay.
Sorry, probably an amateur question, but this data can only be done in the night, or you can't do this in daytime.
Well, you can if you're Hubble. The question was, can this only be done at night? I don't know that there's. Yeah, now, I don't know how much radio you get from cataclysmic variables, but of course, radio can be done in the daytime. Polars and intermediate polars give off tremendous amounts of X-rays. That's one of the keys to figure out that's what they are, and that's from that material streaming in from the poles.
Are there any measurable neutrino outbursts from novas like this?
Neutrino outburst. The answer is yes. And I've read about it just recently, but I don't remember enough to be able to say. But very recently, I think they did see that, and as a matter of fact, it's something that they're kind of hoping they might get a chance to see with T-core board. But not my expertise at all. So, okay, so what else, amateurs? I obviously really enjoy doing this. Why do we do it? Well, first off, as amateur astronomers, visual or CCD, and by CCD I mean CCD or CMOS or DSLR or whatever. But you can contribute in all of those ways. And we can generate these multi-year decade light curves that show these things that have happened over many years, decades, even a century or so. And we, the amateurs, are almost certainly going to be the first ones to see T-core board go up, because we're the ones who are always looking. And there will be pro surveys that will have caught it probably, and they'll be able to go back in after the fact and say, oh yeah, it did happen. But if you're not looking at the data, or you don't have something to trigger, then it's only something you go back and see. And so the professionals around the world have got their target of opportunity proposals already in for major observatories and the Hubble Space Telescope and et cetera, for T-core board, waiting on someone to say, there it goes. And as a matter of fact, the ABSO even has something set up that when someone submits a magnitude estimate that's greater than, that's above 9.5, that's on the way up, it's going to flag everybody at the ABSO to, page them, I suppose. start calling people and.
We have a question for Chris.
Oh, okay, I'm sorry. Do recurrent novae eventually end? Yeah, that's another great question. And I'd even throw another question in, are all novae recurrent novae? But we've only been watching for 100 years. So we've only seen 10 of them go off more than once as a result. But if we watched all of them for, a million years, would they have all gone off more than once? And again, I can tell you with great certainty that we don't know.
100% certainty.
100% certain. So yeah, thanks for the question. And we just don't know. Maybe with this work, we'll help figure that out. Something else we do is, I mentioned the Hubble Space Telescope. Amateur astronomers actually work quite a bit with the Hubble Space Telescope. And I don't mean getting to take the pictures, unfortunately, but we're kind of the ground support team. Quite a few professionals over the last 15 years or so have been working on cataclysmic variables with Hubble. The particular instrument that they use is an ultraviolet spectrograph. And it's the one instrument on Hubble that can be damaged if it's overexposed. And so the professionals put out a request to the amateurs to watch the particular one they're about to use Hubble for, because they want to see that cataclysmic variable when it's low, not in outburst. If it goes in outburst, they want to tell Hubble stop. And so this, I guess 30, 40, 50 variables, amateurs have done this for Hubble. Several times we have called off Hubble because it went off too soon. And the folks at the Hubble Institute want to see at least 1 or 2 amateur data points within 24 hours of letting Hubble make the observation. And they want to see the light curve within a couple of weeks as well before they will push the green light, with the hope that in that 24 hours we're good enough and Hubble's okay.
Has there ever been an incident where
Not yet, but I think there was just a couple of nights ago, there's supposed to be
Is a similar situation with James Webb as well? If it observes something too bright.
I don't know, but you would think so. Yeah.
The web help with this stuff, the infrared,
I'm sure it will, but I will say too, that a lot of the most interesting stuff that's going on in cataclysmic variables is high energy stuff. So it's ultraviolet or X-ray and that kind of thing.
Right.
And the web is good for dust. And so it's not necessarily the perfect instrument. Now there's still interesting things going on. I'm sure they'll work it, but.
Would Betelgeuse, the pulsating of Betelgeuse, because would that be considered as a cataclysmic variable?
Yeah, Betelgeuse, well, at this point, we don't consider it a cataclysmic variable yet.
Despite it, because I read about Betelgeuse, it had surface dust that actually dimmed the star. And that surface dust has actually gone back, and that's where the stars become bright again. Right?
Yeah, it's Betelgeuse, like you say, it has had these big dimming events. The recent one was just shockingly faint. It appears to be dust formation, a lot still to be understood, but we do believe that Betelgeuse will someday go supernova. And it'll be a type 2, it'll be a core collapse. And we don't know when, hopefully not for a while yet. But so when it does go supernova, then it will be a cataclysmic variable.
But until then, it's not, even though you have the surface output varying, it's still not considered as a cataclysmic.
Yeah, and of course, it's just really words, right? I mean, it's not considered a cataclysmic variable just yet, since it's never gone kablooey. But it's a variable star that's incredibly interesting that many amateurs and professionals are working, even if it hasn't earned that name just yet. And we don't really want it to earn that name right away anyhow. Apparently it's going to be pretty powerful. So
we'll need sunscreen.
We'll need sunscreen again. Well, the Betelgeuse screen. So. Did I kill it? I think the next slide is questions. Okay,
This seems, I've seen your presentation before, but you know what, this forum, it's so much better. This seems revolutionary from, just a small number of decades ago.
yeah, it is. We have learned so much. And I tell you, Bill, here's an interesting little anecdote on that for me. Some years, I guess 10 or 15 years ago, we happened to be over in Asia and we went to the planetarium in Hong Kong. And because it's got this planetarium, I gotta go. And they had a little kiosk over on the side where they were showing a little video from the early 70s. And it was talking about all these amazing things that we don't understand that have been recently discovered, like, quasars and pulsars. And as they went through this, I sat there thinking to myself, oh yeah, we figured that out. Yeah, we know that now. And it was really neat to have seen that in my lifetime, where these mysteries from when I was a kid are now things that we know. And I do think about the stuff that are just good questions now, 20 years, and oh yeah, we got that. But they'll have something else for us.
There'll always be more. One answer spurs 10 questions, right?
Yeah, right. So, okay, any other questions?
I have a remark, man, I remember seeing Nova Cygni about 1970.
Yeah, I saw
Did
it.
ya?
I saw it too.
And I think we even got a slide with FBAC from there showing the constellation and that little new star.
That's awesome. Well, and as it turns out, Nova Cygni 1975, it was up by Deneb near the North American Nebula. It's now called B1500 Cygni, and it's a cataclysmic variable that I work from Columbus pretty regularly. It's still doing interesting things. I'm still trying to figure out what these are doing, and so watching Novae post Nova to understand that behavior is important. Some of them go back to being dwarf novae, where they just go off every few days or every few weeks or every few months. And so yeah, I'm actually still watching that one now.
I saw that one, but I didn't know what it was when I saw it.
Oh wow.
Because what happened was I decided I wanted to start teaching myself astronomy. And I got a star chart and I went out and I saw Cygnus would be dead overhead. And I thought, okay, I'll start teaching myself astronomy by learning Cygnus. And I held up the star chart and I got everything to match. And there was this extra bright star in Cygnus. And I was like, darn it, it's like, what the heck? And so then I feel like, oh, well, I don't know what I'm doing. And then I went out like a few nights later, tried again, everything was fine.
You were seeing things.
And then the next issue of Science News arrives and it says brightest nova in more than a century in Cygnus. And it was like right on this night. I'm like, God damn.
Well, he gets all the luck,
Yeah, that's right.
So I thought, but it just confused.
Well,
me.
and I don't know if you know this, Bill, but the guy who did discover it, he got the Nobel Prize. No. So you just missed it. It was just this month.
Literally the first night I decided I'm gonna go teach myself the constellations. The first constellation I picked on the first night to go.
That's pretty amazing. Well, I would suggest that this morning when it comes up, you should go look at T44.
Yeah.
Maybe that'll be enough to set it off.
Of course, I just hear Beetlejuice saying, here, hold my beer.
Anyhow, I guess one last comment is, you can join the AVSO. You can do this kind of work, like I say, with your eyeball in the city, binoculars, getting an observer code to be able to submit your data is available for the low cost of free. And all the star charts are available on the web. All these light curves that I pulled, all that stuff, and about 1 billion times more is available. And I'll put in one last plug. And so the AVSO has been doing webinars and seminars in Zoom for several years now, once a month. And they have been putting them on, they've been recording them and putting on YouTube. You can go to YouTube, and the AVSO HQ channel is loaded with videos on how to do photometry and interesting stars like these and just about everything else in astronomy. And it's also available for the low price of free. So it's a great resource. As a matter of fact, too, Brad Schaefer gave a seminar, Dr. Schaefer, Chief War Warfare, he gave a seminar in September. About an hour and 10 minutes he talked, and then we had 45 minutes of questions. And that's out there too, and he goes into way more depth, and he's a very charismatic speaker. It's a good listen, and so.
When I was doing asteroids, Bill Dillon would give me like when you go out to shoot asteroids tonight, first, you must shoot these 5 fields for me. So
Yes.
I got like, T-Pix again.
T-Pix, I was gonna say T-Pix is one of those recurrent Novae,
Bill.
and I remember Bill Dillon working
Last
on
day was
T-Pix.
T-Pix. I don't know how many times I shot T-Pix for Bill.
Yeah, I think it went off last in 2011, I think.
Yeah.
So,
And
okay, well, if there's more business, I'll let you guys go. Thank
I
you.
like that HLCMA.
So we're gonna go to the finance materials.